So thank you very much. Yes, so this is a joint work with Valentin Blomer, Jörg Brüdern, and Ulrich Derenthal. And good, so I'll start by telling you what the Manin-Peyre conjecture is. So let X be a smooth Fano variety. For example, over the rational numbers, but it could also be a number field. And Fano variety means that the anti-canonical divisor is ample, and this is a projective variety. Okay. And now we need a height function. So a height function is a function from the rational points to the real numbers. This will be an anti-canonical height function. And I'll first tell you what the standard height function is on projective space. So small h from the rational points of some projective space to R. And now if we take a point, rational point, then we can always choose A1 to AN to be integers and coprime. And if we choose coordinates like this, and every point has such coordinates, then we can take the maximum of the absolute values of these coordinates. So this will be a well-defined function, and this is the standard height function on projective space. And if now we take an embedding of X into a projective space, an anti-canonical embedding, which is possible since the anti-canonical divisor is ample, then an anti-canonical height is, yes, this goes first with this embedding into Pn, and then we take the standard height function. So of course, because there can be many embeddings, there can be many anti-canonical height functions, and actually there are also more abstract ways to define height functions, but for us this will be enough to do it like this. Okay, so this is the height function. And now, for an open subvariety U in the Fano variety X, let NXUH of B be defined as follows. This is the number of points, rational points, in this open subvariety, such that the height is smaller or equal to B. Yeah, so B is a real number here. And this is always a finite number. And yes, in this way we can count. Here we count points of bounded height. And the conjecture, Manin's conjecture, says that there exists a U and a constant C greater than 0 such that this number is asymptotically CB log B and log B to the power rank of the Picard group of x minus 1. Okay. So I will put this a bit more upwards. So why is it called the Manin-Peyre conjecture? Well, Peyre gave a prediction for the constant. This is then called Peyre's constant. And so in the original, as stated here, version, U is an open subvariety. And Bartirev-Schinkel found a counterexample. And then Peyre suggested that instead of an open subvariety, one should consider complements of thin subset. Complements of thin subsets. So, but for the examples we will consider in this talk, we will in fact always be able to find an open subvariety where Manin's conjecture holds, where this asymptotic formula holds. Good, and if X is a singular variety, then the formula does not work as it's written here, but there is a modified conjecture by Bartirev and Manin. So for singular varieties, we get an asymptotic CB to some power and log B to some other power. And these powers will be somehow determined by the geometry. But we will only consider smooth varieties for now. Good. So known cases of Manin's conjecture is there are varieties that can be where the conjecture can be proved using the circle method. This was done by Browning and Heath-Brown. If the dimension of X is much larger than the degree of the variety, so in fact they require something like this. Then there's a method to prove it using harmonic analysis on adelic points. And this can in principle only work if there is a dense G orbit for some algebraic group in X. But also here there are only some classes of varieties where this has been done. This has been done for flag varieties by Franke. Yeah.
We cannot read the right side of your paper. Maybe you want to move it. Yeah, perfect. Thank you.
Good. It has been proven for flag varieties by Franke, Manin, and Schinkel, for toric varieties by Bartirev and Schinkel, then more generally for toric bundles over flag varieties by Strauch and Schinkel. And then there are some results for wonderful compactifications. Not for all of them, but for some, by Shalika, Taklu, Bikesh, and Schinkel. Another paper by Gorodnik, Macouron, and O. And for finally for equivariant compactifications of the additive group by Chambalois and Schinkel, and generalization for B-equivariant compactifications of unipotent groups by Shalika and Schinkel. So here, these classes of varieties are actually spherical varieties. I will tell you more near the end what spherical varieties are. And okay, here for these special cases, there's a general proof of Manin's conjecture. So, but if there are no additional, if there's no additional structure on the variety, then there are only few results. So for smooth varieties, for smooth del pezzo surfaces, which are the varieties of dimension 2, there is a result of for 2 del pezzo surfaces of degree 5 by de la Bretèche, and the other one by de la Bretèche and Fouvry, and one of degree 4 by de la Bretèche and Browning. And other than that, there is just a proof for a quadric bundle in P3 times P3 by Browning and Heath Brown. So for singular varieties, there are more examples. For singular varieties, but it seems that counting points using analytic methods is easier if there are singularities. So there are more examples. But now it would be good to prove, of course, Manin's conjecture for the other del pezzo surfaces, but actually it's quite difficult. So if you would be able to, the next thing would be a cubic surface. If you can prove Manin's conjecture for a single cubic surface, I think this would be quite good. Unfortunately, it's difficult. So what we did instead, well, after surfaces, we can look at threefolds. And for threefolds, we have a classification of Fano threefolds by Iskowski and Mori-Mukai. And okay, there's a list, and we could look for some examples there. And the toric varieties are already done because there's a general result. And so we could look in the list for spherical varieties. I didn't tell you what spherical varieties are, but for now we do not use any structure on the variety. And so we look for the next easy examples in the list. And fortunately for spherical varieties, there is a classification. It's in Johannes's dissertation. And there we have a list, and we try to prove Manin's conjecture for those varieties in that list. But for now, I won't tell you anything about the varieties at all at first. I will tell you what our approach in proving this is. So the paper has 3 big parts. The first part is geometric. The second part is analytic number theory, and the third part is then applying the results from the first 2 parts to the examples. I will talk mostly about the first part. So the first part is the geometry, and I will talk now about Cox rings and universal torsos. So if X is a normal projective variety, with finitely generated divisor class group, of X, which will be equal to the Picard group if X is smooth, and we only consider smooth X for now. Then the Cox ring is defined as follows. We take this sum over all these sections with divisor D, and here we go over divisor classes. So, and here we get a vector space, of course, first, and then you have to define a multiplication, and you can check that it is possible to define a multiplication in a compatible way, and then you have a Cox ring. And so in the spectrum of this Cox ring, if this Cox ring is finitely generated, algebra, finitely generated, then X is called a Mori-Dream space, and then we have this construction that inside the spectrum of the Cox ring there is an open subset of codimension at least 2, and this is the universal torsor. And here we get a quotient by some quasi-torus, and the quasi-torus is the spectrum of this group algebra with the class group. So this is a quasi-torus where the character group is the class group of X. So, and the easiest example is if you have projective space, then the Cox ring will be the polynomial ring, because this is just direct sum class group is integers greater than 0, and here we have the sections, and this is then just a polynomial ring. And the quotient is an plus 1 without 0. So this is the universal torsor over Pn. So, and it is an empirical observation or something, I would say, that it's easier to count rational points here instead of here. But the real reason, not really reason, it's just an observation that it can often be done. So, for example, if you have the Petzl surface of degree 8, that will be a toric variety. The blow up of P2 in one point. Then we have homogeneous coordinates of P2. And we take a point, we take this point where y and z are 0. And we have an exceptional divisor. And we introduce a coordinate for the exceptional divisor. And then the Cox ring will be a polynomial ring in these coordinates. And the divisor class group here of the blow-up, of course, has rank 2. And then we have degrees of these variables. So depending on the choice of the basis, we could have degree 1, 0, 1, minus 1, 1, minus 1, and 0, 1. And the universal torsor here is A4, of course, with 4 variables. And we have to remove a closed subset, and here's a 0 set of y and z, and of x and w. And then we get a quotient by a 2-dimensional torus, and here we have the blow-up of P2. So, and so this is a toric variety. The blow-up of P2 in one point is a toric variety, and if you have a toric variety, it's quite easy to get this always. So for a toric variety, there will be a fan For example, the fan of this blow up looks like this. We have here one ray for the P2, and here we have a blow up, so we have another divisor. Okay, this is the fan of the toric fan of the blow up of P2 in one point. And to each ray will correspond one variable in the Cox ring. And you can get this set that you have to remove by taking the minimal subsets of variables which are not contained in a cone. So here, for example, W and Z are contained in one cone, but W and X are not contained in one cone. And that's why here you have to remove the set, the zero set of W and X, and the same for Y and Z. So for toric varieties, it's easy to get the universal torso. This was done by Cox, and that's why these rings are called Cox rings. So here we have the fan of P2. So here it looks a bit complicated. You have the blow up of point in P2, and in the Cox ring we get the polynomial ring. So polynomial ring is quite easy. But for example, if we take the Petzler surface of degree 3, cubic surface, then cubic surface is cubic surface in P3, for example. Maybe this does not look so complicated. Yeah, it's an equation. But the Cox ring then has 27 generators, and usually relations generated by quadrics. So this was done by Stillman, Testa, and Velasco. And so even if the Cox ring looks complicated here, one would assume that to solve Manin's conjecture, one should attempt to count the points here using the Cox ring. But it's very difficult here and has not been done. But if anyone manages it, it would be a great result. But we are not doing this here. This is just an example. So the difficult cubic surfaces. So we go back to the easy case of toric variety, which has a fan. And so how do we get the height function? Well, the height function we can do the following. We look at monomials in the Cox ring, monomials in the Cox ring of degree minus kx. This is the anticanonical divisor, which is a degree in the class group. And we take all these monomials, and we can get them using methods from toric geometry. We can take the polytope of this span here and take the dual polytope, which looks a bit like this. Then the number of anticanonical monomials, which the only ones that we will need is those corresponding to the 4 vertices here. So in our example, x squared y, here we have y3 w2, here we have z3 w2, and here we have x squared z. So yeah, here in each case, so for example, for each cone here, for example we have a cone, this corresponds to an open subset of the toric variety, and to this corresponds the monomial, which has only variables x and z. So for each maximal cone here, we get one monomial which does not contain the variables occurring here. So, and we can take these monomials and define a height function. Now this height function will be on the universal torso. And actually here we have to look at not at rational points, but at integral points. So we take integral points. And here we take the maximum of these monomials. And then we have to divide by the GCD, because you remember that in the first part of the talk, we had to choose the coordinates integral and coprime if we take a standard height in projective space. And so another way to do this would be to divide by the GCD. But actually, we have A4, and we have to remove this closed subset here. And if we look at integral points, this is this corresponds to having GCD conditions. So actually, the integral points on this open part are actually the points where these coordinates have satisfy the GCD conditions. GCD of y and z is 1, and GCD of x and w is 1. And then it's an easy exercise to see that if we have these conditions, then this is always 1. And so we can disregard this completely. And now the height function looks quite simpler. And now the counting problem. Is that the number of points of height b is 1/2 the number of x, y, z, w in set 4 without 0, because we take as u in x the open torus. That's where the not equals 0 comes, such that the GCD is 1 for these conditions, and the maximum of these monomials that we have up here is smaller than b. And so this is the first part to get this counting problem. And the second part is now to get an asymptotic formula by counting these points. So now comes the analytic number theory. And in this case, for toric varieties, it's not difficult. We approximate this number by an integral. This is the volume, and here we have these height conditions. And all coordinates should be greater than 1. And so this number is this plus an error term. And the error term is small enough. And so here, for toric varieties, that you get an error term small enough can be done by elementary methods. And this volume here will be what we want, CB log B. And then we still have plus the error term small enough. And so why do we have this counting problem here? Well, if we look back at the universal torso, so here we have a projective variety. So rational points are the same as integral points. So we can count integral points, and here we have integral points. And if we look at integral points, this group will be plus or minus 1 to the second power. So here we will have four elements. Oh, sorry, this is not 1/2. This is actually 1/4, because this group has 4 elements. So what we have to do in the first part, we have to prove that this, what we have written down here, is actually correct. That we have a 4-to-1 correspondence between what is written down here and the number of rational points on the variety. And in the second part, we have to count this using analytic number theory and get the asymptotic formula. And in the first, so this for toric variety, this was an example of a toric variety. This has been done for toric varieties in general, for split toric varieties over Q, split smooth toric varieties over Q by Sahlberger. But for some of the other examples where Manin's conjecture is known for examples, in each example, there has been a proof that we get a good counting problem and then the second part. So, and in our paper, the first part, we want to see how far we can make this a bit general so that we can get the counting problem for some varieties in an automatic way. And for the second part also, in very special cases, there are also some results that then you can use this. And in particular then for the smooth spherical Fano varieties of dimension 3. But we are not done yet for all of them, only for half of them, but I will come to that later. So we have seen this and this. And now I will show you our first result. So let X be a smooth split projective variety over Q with minus kx big and semi-ample and Picard group free of finite rank. Assume that the Cox ring is finitely generated and that the Cox ring is a polynomial ring divided by one relation only. And this is one relation. So such a Cox ring gives us a canonical toric embedding into toric variety Y0. And there exists a projective completion, maybe more than one, of Y0, which we call Y, such that the Picard group is still of X is the one of Y. Actually here, this if Y is smooth. If it's not smooth, then here we have just the divisor class group. And yes, the Cox ring of this toric variety is actually just a polynomial ring without the relation. So by result of Hu and Kiel, a projective variety where the Cox ring is a polynomial ring is actually a toric variety. And yeah, so these variables will be in bijection with the rays of the fan sigma of the toric variety y. Okay. And put this up. So this is the Cox ring, but we need the universal torso. So we need this open subset or the closed subset that we have to remove. So we call S1 to SR subsets of the coordinates minimal subsets such that they are not contained in a cone in the fan. The rays corresponding to this. So to each coordinates will correspond some rays, and I do not I do not distinguish between the rays and the coordinates here. Maybe it's a bit sloppy, but so this is what we take. And now the first theorem. Which has a few conditions. So we assume that y is smooth. And we take u to be the torus, not the torus, the intersection of the torus with x. So in this subvarieties, this will be x without these divisors given by the coordinates. Then this h here going from rational points on x, we take a point and we send it to the maximum. And here we take a monomial of x hat, and m goes over all the monomials of degree minus kx. And monomials in the variables x1 to xj in the Cox ring. So here we take this maximum. And yes, x. Now we have to, in these monomials, we have to kind of put in a point x directly. We have to lift the point to the torso. So we take x1 to xj such a preimage of x. And we can always lift this under this also such that the GCD of all these subsets of variables is 1. So, and one thing that we say is that if we take this h, this is a well-defined height function. And we get a nice counting problem. The number of rational points of bounded height is 1 divided by 2 to the power the rank of the Picard group of x times the number of integral points subject to these conditions. The equation should be 0. So here we have to then take integral coefficients of the relation, but we can always do this. The maximum over all the monomials of anticanonical degree should be smaller than b, and the GCD, we have these GCD conditions. Okay. So this is, and here we have a closing brace. So this is this result. So if you look back at the, so here we have some GCD conditions, and I didn't talk about the constant. So actually, this is not quite correct what I wrote here, because the constant is missing. So, but actually, if you take the GCD conditions or not, it will only change the constant in some way. But if you do everything correctly, you will get the right constant and so on. So in addition to this theorem that is here, we also have a result that says that the constant, Peyre's constant, actually comes out correctly from the Cox string as well, in addition to this. But this is basically the main thing. So this is the first part. And when we have a counting problem, then there's a second part. Where we say let X be a smooth split spherical Fano variety of semisimple rank 1 and type T. So I didn't tell you yet what this is, but if you look in the list of Johannes Hofscheier, then there are several types of spherical Fano varieties of semisimple rank 1. And for these plus some easily checkable conditions, which are true always in dimension 3, then the Manin-Peyre conjecture holds. For X. Okay, this is the second part. So I will now first go back to the first part and tell you how this is done or what we would like to improve in the future. So to do this, actually, you so it is well known that if you have Mori dream space, then you can you get this embedding into a toric variety Y, and then we can do everything in Y using as Sahlberger did and using this embedding. But here we have some conditions. Here we assume that Y is smooth, for example. And here we assume that the Cox string has only one relation. So for these varieties, for spherical Fano varieties of semisimple rank 1, we always have one equation in the Cox string here. But already there are some examples, but they do not have type T, so they are not included in this theorem, where we cannot choose Y to be smooth. So I will show you this in the toric picture again. Where do we have it? So the problem here is where's the picture? Okay, doesn't matter. I'll write a new picture. So there is a well-known result that if X is smooth, and we take this embedding into the toric variety given by the Cox ring canonical embedding, then this open part here will be smooth. But smooth over Q. But now if we want to use this universal torso method, we have to take integral points on the Cox ring. And then what can happen is that, okay, we can, it would not be very bad if after completion this is not smooth, except for the problem that some integral point here could land in the not smooth part of the toric variety. For example, it could be that we have some point which will be smooth in the smooth part over Q, but over some prime not. Because for the toric variety, you can see in the fan where it's smooth or not. And even if you have a toric variety, split toric variety over the integral over Z, then you could, this could be not here, but you could have a non-smooth cone here in some high dimension. And then a point XP could be in this non-smooth part. So this is the problem which we have not solved yet, but we hope that in a later version we can remove this condition that the ambient toric variety must be smooth. And the other point is that the Cox ring is given by one equation. That's very special, of course, but we hope at least that it's not too difficult and only maybe to write it down nicely, that we can replace the one relation at least by a complete intersection. Several equations, complete intersection. But this is also a question mark for now. And then where we have this analytic number theory thing, when we count the points, so I'll tell you a bit about the spherical varieties of semisimple rank 2. That means that we have an algebraic group SL2 times the torus, which acts on X with an open orbit for a Borel subgroup. Of Borel subgroup of G. And if we look in the what can happen here is that the Cox rings are always given either by something which we are not interested in because Manin's conjecture is already known, or it has type T, which means that the equation looks like this. And or of type N, where it looks like this. And so actually, for these varieties, this theorem works. But actually, if you look in the paper, there's a theorem which is complicated to write down, where there are some conditions, but they're very, very, very special. For example, you need one equation. It has to look like this, And in addition, there's some additional things that can be checked easily. And if you can check all of these things, then the Manin-Peyre conjecture will be true. And so this goes in the direction that, yes, we want to have some results in there so that you can easily see if you have a new example, if it's included there, then it's already okay, and then you can filter out the more difficult examples. So this is has been done by our experts in analytic number theory. I'm still in the process of learning how this exactly works. So I will not talk much about this second part. And so we have this first part, the geometry, and the second part, counting of points. And in the end, we apply these two theorems to these examples and see that they all work. And what is missing is the spherical varieties of missing from this list, the ones of type N that have this kind of torso equations, which we hope to be able to do later. So I think I am finished here. Yes, thank you very much.